thank you, Kumar. And quick question, sorry, I missed the sessions earlier. Do you prefer to sort of answer questions for speakers to answer questions on the fly or wait till the end, or do you not?
On the fly, while you're presenting has worked the best, because otherwise they get stale. Yeah.
Okay, cool. I'll try to watch the chat then. All right. So thanks very much. My name is Brian Friesen. I work at NERSC, the National Energy Research Scientific Computing Center, which is a national user facility located at Berkeley Lab. I'm very happy to be here. Thanks very much for the invitation to come. I'm excited to share some details about the Perlmutter system and its architecture and configuration with you all. I like this. This picture is our building. Actually, we moved here into this building in 2015, December of 2015. It's got a nice view, as you can see. That's the University of California, Berkeley campus there. Down below, you can see the clock tower on the bottom left of the screen, and then there's San Francisco off in the distance in front of the sunset. So it's a great building. I really enjoy being there. And the data center, you can't really see in this picture, but it's actually located just below where this picture is cut off. And from where this is taken, it's actually standing basically on top of the cooling towers. There are 7 cooling towers for the Perlmutter and Cori systems that we have. Okay. So as a summary, this is a summary of where Perlmutter is at the moment. The configuration, as you might know already, it's heterogeneous in a couple of ways. One way in that it will have 2 different types of nodes in the system, and then the other way is that the GPU nodes have both CPUs and GPUs on them. And so it's a heterogeneous system. It was designed from the ground up to focus on accelerating scientific workflows, in particular sort of data-centric workflows, and I'll talk a little bit more about what that means in a minute. It's the first phase. The system is being delivered in phases, which is becoming somewhat common in procurements of such large systems in recent years. The first phase of the system is already here. It's already on the floor. There's a picture of it on the right side of the screen there. The first phase has all of the GPUs in it. So the GPUs came first, which is really exciting because the GPUs provide most of the performance that the system will provide to our thousands of users. The GPUs are the new A100 GPUs from NVIDIA. So it's a fairly new architecture. I think it was just released, I think last year. And there's 6,144 of them, plus a handful more on some login and service nodes. So there's a lot of GPUs, a lot of performance capability in the system, and we're excited for users to get on it soon. And hardware is nothing without software, and I'll focus mostly on the hardware, of course, for this presentation. But in terms of software, the system will provide programming language support for programming languages and models of quite a wide variety to ensure that our many thousands of users are able to use the GPUs on the system effectively. Okay. I see there's a question already. Why are there GPUs on the login nodes? Let's come back to that. It's not a very interesting answer, and I don't actually. Yeah, we'll come back to that. So hold on to that. So before we get into the architecture, I think it's useful to put NERSC in context. Buying a system and designing its architecture and so on doesn't happen in a vacuum. We don't just get a pile of money and then go build whatever we want. NERSC has a mission, which is defined pretty precisely by the Department of Energy. And in particular, our task is to accelerate the scientific workloads and maximize scientific productivity for over 8,000 users who get either funding or computing time from the Department of Energy Office of Science for doing their science. And so we've got, like I said, 8,000 users, around 800 projects. A project is basically, you can think of as something someone wrote a proposal for and the proposal was accepted. So there's a very large number of different scientific campaigns going on that use NERSC resources. There's about 700 different codes. That number goes up quite a lot if you count, very small codes that are much smaller, but the sort of workhorse production codes are number around 700. And we facilitate a lot of scientific productivity. I think it's closer to 2,500 NERSC citations per year in scientific journals. So when we design systems, we have to think about all of these users, all the science that they're doing, all the codes that are running. So it's a pretty delicate balancing act that we have to manage when we design systems like this. And for many years, NERSC has supported sort of traditional simulations, there's some examples on the top right of your screen there. And more recently, we've focused more on integrating NERSC capabilities into existing scientific experiments that are also funded and managed by the Department of Energy. And that has led to some unique design decisions for the system as well. And for a little bit more context, this is some recent history of the production systems that NERSC has deployed over the last decade or so. And you can see we've gone from sort of traditional multi-core CPU systems, which is Edison there on the far left, where we had relatively low core counts, but each individual CPU core was quite powerful. Cori was a mixture of those sort of multi-core CPUs as well, with high throughput single thread performance, but also a large number of many-core processors as well. These use the Knights Landing architecture, which is also on the Theta system at Argonne. And Perlmutter's up next, so that's what's coming now. And this is the first production system that has GPUs in it that NERSC will deploy. So that's very exciting for us. It's a lot of work to make a system with GPUs accessible and usable to such a large number of users, but I think we'll manage it. And then finally, the successor to Perlmutter, we expect will be an exascale class system that'll come sometime in 2024, maybe a little bit after that. But you can see the performance of these systems going up quite a lot as you go from left to right, but the power consumption is actually not going up too much, which gives you a good indication of how power efficiency of processors has really improved over the last decade, and even long before that as well. Okay, so now let's get into the Perlmutter architecture itself. So this is a very high level overview of the architecture, and it also there's also some time, there's a dimension of time in this plot as well, in that we've colored certain components of the system based on when they're arriving, since, like I said, this is a phased delivery of the system. What is already on the floor are the boxes that are colored green, which are the GPUs. All the GPUs are here. Our new all-flash Lustre file system is also here, so that's 35 petabytes of all-flash running at very, very high bandwidth and high IOPS of 5 terabytes per second of bandwidth, maybe even more than that. And the connectivity to our existing file systems, which are mainly the long-term file systems mostly for data storage. They're more designed for storage and redundancy than for performance, and so that connectivity is already here as well. There's sort of a mixture of things that are coming in the near future, which include there's also a few thousand CPU-only nodes that are coming in the future. We don't have those yet. There's also, we have some of the login nodes, the things that you'll log into when you first SSH into the system. Some of the workflow nodes and high memory nodes are here. And then the so-called slingshot interconnect is also partially configured, but will be improved with a future phase. So I see a question on the bottom. Do you expect Perlmutter to climb on top 500 after phase 3? Yes, and I can't go into too much more detail than that. Unfortunately, one of the challenges of presenting a phase delivery system is that not everything is public yet about what exactly the system will contain. But the answer is yes, it should improve. Okay, so I really like understanding not just system architecture, but actually how they're built physically. There are some really challenging design decisions that have to be made if you want to build a system with such high compute density and with some brand new technology in it. So this is a picture of this is the front, actually. This is what Perlmutter looks like when the cabinet art is not on it. So actually, I think in my Zoom background, you can see the cabinet art. And if you open those doors, this is what you'll see. So there are Perlmutter phase 1 is 3 rows of 4 cabinets each. So you can see on the left, that's 1 row of 4 cabinets, and then there's 2 more that look just like it. The tubes are water. So this is the first water cooled. No, actually, that's not true. This is a water cooled system that we have. The compute density is so high that you can't keep the parts cool just by blowing cold air on them anymore. So there are cold plates that connect to different components of the compute nodes in the system. And as you can probably guess, the blue tubes contain the input water, so they come in from the water towers outside. They cool the components, and then the red tubes carry the exhaust water out to be recycled. An interesting feature of this is that although we have cooling towers, we don't have chillers. There are no chillers in the system, and the reason we don't need those, the reason we can get away with that, is mostly because the climate of Berkeley in the Bay Area in California is such that the ambient temperature outside for most of the year is cool enough that just by running the water through the cooling towers, that's sufficient to keep the water cool enough. Okay, so this is what the back of the compute of one of these cabinets look like. This is actually only half of a cabinet. These are the switch blades. So the front, you could see all the compute nodes. And in fact, I forgot to point out an interesting design decision of this is that the compute nodes are actually mounted vertically. They're not horizontal as you normally find in sort of standard 19-inch server racks. They're actually mounted up and down. But the switch blades in the back, which plug into those compute nodes in between, they are mounted horizontally. And there's actually a very clever reason for doing that, which I'll get to in a little bit. But what you can see here, all the connectivity here is these are copper cables. These switches, as you can see, are not fully connected yet. This was sort of in the middle of installation. But the high-speed network that Perlmutter will uses a combination of copper cables or electrical cables, which is what you see here, and fiber optic cables, or they call them active optical cables. And the active optical cables are not in this picture, but I'll talk about those in a minute. And I think you actually had a presentation on some of the differences between those two types of connections and why systems of this type tend to use a mixture of both. Here is what each one of those compute nodes looks like. So each one of those vertical slots it's pretty long. It's about 2 feet long, if I remember right, maybe even a little longer than that. And each one of them has 2 compute nodes. They're stacked front to back. And each one of the compute nodes looks like this, not physically like this, but this is a sort of a diagram of what's contained on them. Each node's has one AMD EPIC third generation EPIC, whatever Milan is. It's a Milan processor. I forget what generation of EPIC that is, but it's a 64 core, very powerful CPU, one socket of CPU connected to 4 NVIDIA A100 GPUs that you see on the bottom. The connection between the CPU and the GPUs is PCIe 4.0, 4th generation of PCI Express. So you can see from the bottom there are the bandwidths per connection listed there. So about 30 gigabytes per second per direction connectivity between each GPU and the AMD CPU. The GPUs themselves are connected with the 3rd generation of NVLink. And what's really neat about NVLink is that you can actually bond connections together to get higher bandwidth. And in fact, I think you can bond up to 12 of them together I think each GPU supports up to 12 NVLink connections. We don't use, we don't have 12 between each GPU. We actually have 4, but you can see if you add them all up, you can get to 12. And so you end up with that much connectivity. I think you end up, I have it there on the bottom. You end up with 100 gigabytes of bandwidth, 100 gigabytes per second per direction of bandwidth to each of the GPUs. And they're connected all to all. This is not NVSwitch. There is a separate NVIDIA product, which is called NVSwitch. There's not NVSwitch on these nodes. This is just pure NVLink connectivity. There are few enough GPUs on these nodes that you don't really need NVSwitch to get this kind of connectivity and bandwidth. And then at the top, and then we have, there's a lot of, I think it's either 256 or 512 gigabytes of DDR4 memory, of host memory. Each of the GPUs has 40 gigabytes of HBM2. So there's about 40 times 4 is 160 gigabytes of memory on the GPUs, and then something like 256 or 512 on the CPU. I forget which one it is. And finally, the connection to the high-speed network is done in phase one. The connection to the high-speed network is accomplished with two Mellanox ConnectX-5 HCAs. They're called host channel adapters, and that will change in a future phase of the Slingshot network. But that's what we have for phase one. So this is what was used for the top 500 score that was mentioned in the chat just a few minutes ago. So I see one question here. Do you expect AMD to take a big chunk of the top 500 systems away in the next few years? I won't comment on that. I acknowledge the question. It's a very interesting question, but that's probably for someone else to answer, unfortunately. Why AMD processors and not, okay, why AMD processors and not AMD GPUs? It's a great question. We've certainly thought about that. Some of those decisions, unfortunately, I don't think I can discuss in too much detail, but you can imagine that decisions like that involve a lot of things, which include performance, price, how much software there is that can support all those different things. And different sites will make different decisions. They evaluate each of those differently. But NERSC made the decision to focus on NVIDIA GPUs. Okay, in the diagram, the only connection with the interconnect is through the CPU is yes, it is. So the question is GPU direct RDMA not supported? It actually is. I actually have a whole slide on that. So thank you for teeing me up for that. We'll get to that in just a few minutes. To compare the GPUs in a little bit more detail to their predecessor, I've made this table here. Most of the stuff on the right I already mentioned, most of the stuff on the left I already mentioned. What's on the right, I think, shows you just how much how much NVIDIA has improved their GPUs from the Volta generation, the V100 generation, to the A100, and it's impressive, to put it mildly. The memory bandwidth has gone up a lot, by about 50%. Similarly, the memory capacity has more than doubled, gone from 16 gigabytes to 40 gigabytes. The caches and shared memory per SM have gone up by quite a lot too. The number of SMs has increased. And what's really neat about A100 is that this is the first generation of NVIDIA GPUs in which the tensor cores actually support full FP64 inputs and outputs. And that's why you see the parentheses in that top row. We actually count the FP64 peak differently depending on whether you have those tensor cores turned on or not. V100 also had tensor cores, of course, but they were limited, I think, to 32-bit, to FP32 inputs and outputs, even though the actual computations were done in lower precision than that. So that's a really exciting innovation for the A100 GPUs. There are many codes which are not ready to use. A lot of code developers are thinking about using mixed and reduced precision in their algorithms, but in production, many codes are not able to do that yet. They still require full FP64. And so by enabling FP64 inputs in the tensor cores on A100, that I think will open up the capability of tensor cores to many more applications that run at NERSC than could have previously with V100. Okay. So you had I saw there was HPE gave a talk earlier about interconnects. So this was probably somewhat of a review for you. I won't go into too much detail here in that case. But like I said, the high-speed network on Perlmutter is the product is called Slingshot. It's an Ethernet compatible high-speed network. There are a lot of neat innovations about Slingshot, but one of them is that you can connect almost every type of node on the system to the high-speed network. And that is a significant improvement over the previous generation of supercomputers that Cray at the time had been developing, which is XC, which is what Theta is, and also what the Cori system at NERSC is as well. With XC, XC also had a high-speed network, of course, but which was called Aries, but it had a very specialized protocol, and there were as a result, only special types of nodes could use the high-speed network. Not everything could. Slingshot has changed that, and now you can connect many more types of nodes into the high-speed network, which will enable a lot of innovations that we're looking forward to using. The topology of the network is, as I think you learned already, is called Dragonfly, and I won't go into detail about what that is. There's a little diagram there on the right. It's essentially a hierarchy of all-to-all connections, and the reason it's done that way is essentially to maximize connectivity and to minimize the number of long fiber optic cables that you need, because fiber optic cables are incredibly expensive. And so but they're also very useful because they can carry very high bandwidth, very low latency, and they can be very long, physically very long, whereas copper cables cannot. And so Dragonfly attempts to balance cost and performance together into a single solution. Okay, so this is another comparison of how the supercomputers that Cray made most recently with the XC product line have changed with Shasta, which is what Perlmutter and also some of the exascale systems are as well. So on the right you can see this is a physical diagram of the compute nodes on XC. So on Cori or Theta, this is essentially what it looks like if you sort of peel the cabinets apart and you just got to see the compute nodes stacked together. On XC, the switches into the high-speed network were parallel with the compute nodes. They're all mounted horizontally. And one of the consequences of that, which I won't go into a lot of detail about, but one of the consequences of doing it that way is that you had to attach what's called a backplane to those switches in the back, so that you could get all the connectivity that you needed, both to other nodes in the same what they call electrical group, and also across groups to all the other pairs of compute nodes in the system. And so that's what it looks like. That's what XC looks like. By contrast, like I pointed out a few minutes ago, in Perlmutter, the compute nodes are actually flipped horizontal, or excuse me, they're flipped vertically. And so they actually connect. So the compute nodes are vertical, but the switches are still horizontal. And what that allows you to do is you can actually connect all the switches to all the compute nodes without cables, within a cabinet, I should say, without cables and without a backplane. So there are fewer parts to paint this picture very broadly. You don't need a backplane anymore, which simplifies the design a little bit. And there are other, this also enables higher density. You can actually pack more of these compute nodes into these admittedly very large compute cabinets by stacking them this way. Okay, I see a question. Out of curiosity, what's the noise level? See, this is a great question. There's a question about noise. Yeah, so our previous system, Cori, is it's sort of the components are air cooled. So they call them blowers, but they're just fans. These huge fans on the ends of the cabinets and also kind of interspersed between them, between pairs of cabinets along a row. So the blowers draw in air from one side, they blow the air out the other side. And the air cools the components, and then there are heat exchangers that actually there are heat exchangers that are configured such that the hot air that has cooled the components is then cooled by water, and then the water exchanges all that heat. The water draws all that heat, sends it out to the cooling towers, and then it comes back. And the comment is exactly right, that they are incredibly noisy. Those blowers are extremely loud. And in fact, we actually require ear protection if you're in the machine room for more than, I think it's 15 or 30 minutes, because it's so loud. I actually haven't been into the machine room since Perlmutter was delivered, but I imagine it is much quieter because most of the pumps for pumping all that water are actually on the floor below. So most of the I'm sure the pumps make a lot of noise too, but you can put them farther away. But maybe someone who's stood near a system like this can comment with more authority, but that's my understanding. But yes, I imagine it is much quieter being water cooled. Oh, and there are other interesting, I forgot to mention this last point, another interesting innovation of the Slingshot network is that you no longer need what are called LNet routers to integrate your Lustre file system into the high-speed network. So on Cori, on any XC system, you had the Aries high-speed network that connects all the compute nodes together, and then you had a Lustre storage. You had a Lustre storage system, which was physically distinct and actually ran its own InfiniBand network. And there are LNet routers that sit in between them that translate the Aries protocol into the InfiniBand protocol that Lustre understands. With Slingshot, we don't have to do that anymore. Everything is now integrated into the high-speed network. So that's very exciting as well. Okay, just to give you a little bit more detail, watching the clock, just to give you a little bit more detail about storage, because I haven't spent too much time on that. We have very high bandwidth between the CPU and GPU nodes going to our Lustre file system. The Lustre file system itself has it's extremely fast. I mean, we're getting, this is actually an outdated slide. I should have corrected that. I think we're over 5 terabytes per second of bandwidth to the Lustre file system. There are some new capabilities for moving data around between different parts of the system. We have these so-called data transfer nodes, workflow nodes, and they all interact with Lustre in these sort of clever ways that allow users to sort of move their data very quickly and easily so that they can to streamline their scientific workflows. The other, besides just bandwidth, of course, the appeal of an all-flash file system is IOPS, so sort of metadata performance. So the speed with which you can create, touch, destroy files and directories is extremely high, much higher than you could achieve with a traditional spinning disk Lustre file system, which is what we have on Cori right now. You may have noticed that the capacity of our Lustre file system on Perlmutter is not too much higher than it was on Cori even. Cori has a 30 petabyte Lustre file system, and Perlmutter is slightly larger, but not too much larger. And the reason for doing that, there are a few reasons for doing that. Like, there's sort of a running theme in this presentation, which is you have to balance cost with functionality and performance and all those things together. If you wanted to, go increase our Scratch file system by an order of magnitude and use Flash, that would cost a fortune. But what we're able to do instead to provide both bandwidth and capacity is by having tiered storage. And that's kind of what you see here. There's a fair amount of tiered storage even on Cori. And there's the y-axis, which is sort of absent, is the bandwidth is increasing as you go up. So the slowest things at the bottom, and then the moderate performing things are in the middle, and then the very fastest file systems are at the top. So Cori also had some Flash, has a Flash file system on it, which is integrated into the high-speed network. But it's just a burst buffer. It's not really meant for anything more than, much more than the lifetime of your job. It's just for getting extremely high bandwidth onto a disk during your job, and then moving that data off of that Flash onto either Cori's 30 petabyte Scratch file system or into tape or something like that as soon as your job is done. There's not much capacity there for supporting anything larger than that. And so we supplement that with Cori's 30 petabyte Scratch file system. We also had a GPFS-based project file system, which was meant for sharing data amongst scientific projects and groups. That was also fairly small, about 12 petabytes. And then we had our long-term tape archive, which was very large, but as you can imagine, very slow. Perlmutter has sort of continued in that theme and has closed some of those gaps. So the Scratch file system is now 35 petabytes, extremely fast. We have replaced our project file system with what we call CFS, Community File System. This is around, I think it's around 120 petabytes now. It is disk-based. It's also GPFS or spectrum scale, I guess is the new product name for that file system. It's moderately fast, not as fast as all flash, but certainly much faster than tape. But it's very large, and so we're able. So you can imagine your workflow might consist of running your scientific campaign on Perlmutter's scratch file system, and then moving that off to the community file system for post-processing or something to that effect when your job or when your science campaign is done. And we will continue to have our tape archive, of course, and that's not going anywhere. And in fact, it has grown quite a lot in size. I think it's closer to 250 petabytes now. But most of these capacity gaps, have been closed as we've moved from Cori to Perlmutter. And that's very important because you can have all the performance you want, but if you have nowhere to store your data, or if moving your data takes as long as as producing the data did, then that doesn't do you a whole lot of good. So we've attempted to balance all these different constraints in a way that will make the system both very fast and also accessible to a wide variety of scientific campaigns. Okay. So that's most of the hardware. I have a couple of slides just about software, just to give you a taste, but I won't go into too much detail. Like I said, we have the system will support a large number of programming models. If you've not heard about, I guess we're in track 1 now, but I imagine you'll hear much more about some of these languages and programming models in the coming days. But you can see we're trying to support as much as we possibly can, and what's not being supported by vendors, NERSC is trying to support ourselves, or through some combination of NERSC and a community effort. And I won't, like I said, I won't go into any detail about this. It just gives you a taste of the variety of things that we would like to support on Perlmutter. Someone asked about GPU Direct, and I have a whole slide about that. So we do have GPU Direct. It is absolutely supported, and we've used it quite a lot already in testing since the system has been installed. And the system is here. It's not available to users yet, but it's been alive. It's been powered up, and we've been testing it pretty heavily for the last several weeks and months. And GPU Direct itself is actually a family of technologies that NVIDIA has been cultivating for quite a long time. There's a lot of different expressions of GPU Direct. There's peer-to-peer, there's GPU Direct storage. GPU Direct RDMA was the one that was mentioned in the comments earlier, and that's absolutely supported on the GPU nodes. So the way that GPU Direct works is essentially when you want to copy some data that's in GPU memory on one node into GPU memory on another node, without GPU Direct RDMA, you have to copy it to the host, to host memory, CPU memory, then copy it to the NIC or the HCA, and then basically do the reverse process on the other node that you want to copy the data to. GPU Direct RDMA is a capability that combines some technologies of NVIDIA GPUs and Mellanox HCAs. I guess they're now NVIDIA HCAs as well, and allows you to bypass CPU memory altogether. So you copy your memory directly from your GPU buffer, your memory buffer on the GPU directly to the HCA, and then the reverse on the remote node. So that cuts out one step of copies in your data motion, which improves performance, it lowers latency, and there are quite a few codes that I expect will be able to take advantage of this. And most of this is actually implemented sort of for you in Cray MPI. You don't have to program this very explicitly into your code that you want to use this trick. When you call your different MPI functions, if the constraints work out just right, the MPI runtime will do this for you. Okay, another cool element of Cray MPI is that it's CUDA aware. And so what the CUDA aware essentially means that you can put pointers to GPU memory into an MPI call, and the MPI library or runtime will just do the right thing. So without CUDA aware MPI on the top right, I put a little snippet there. if you wanted to send some data that's in GPU memory to another node, you have to first copy it to the CPU memory with the CUDA mem copy, and then you send it off. With CUDA aware MPI, you just put the you put the pointer to your GPU memory into your MPI send, and you're done, and it just does the right thing. So the snippet on the bottom would crash if you were running on a if you were using an MPI implementation that didn't support CUDA awareness. And on Cray MPI, it supports CUDA aware MPI features like this, and it also will use GPU directive RDMA where it makes sense. But like I said, the one challenge or the one caution with regard to programming to CUDA aware MPI is that because it's not standardized, so the MPI specification is silent regarding whether CUDA awareness should or shouldn't be supported, or at least it was in version 3. I'm not sure about version 4. I haven't read it. But there is a chance your code may be less portable if you're doing it this way. Like I said, if you move your code that relies on CUDA aware MPI onto a different system that doesn't have that, then it may crash. It's just something to be aware of. Okay, and as you might expect, the Perlmutter GPU nodes also support CUDA unified memory. This has been around for many years already. There are a lot of implications of unified memory, and one of them is that you can do clever things. Well, the CUDA runtime will do clever things with memory that's allocated with this CUDA malloc managed function, where you can dereference pointers on CPU in CPU or GPU memory, and if the memory has been allocated with CUDA malloc managed, then the CUDA runtime will just move the data back and forth for you. And so it ensures consistency. It's also very convenient, especially if you're porting a pure CPU code to the Perlmutter architecture that has GPUs on it. The one challenge is that it doesn't necessarily guarantee any kind of performance, because it's only going to move memory, or I think it's only going to move memory as soon as it's demanded by the device that needs it. It won't try to guess ahead of time where it needs to go. So if you want to move memory, so if you want to hide communication and computation, which is an important concept that I'm sure will be covered at length in this conference or in this workshop, then this you might need to supplement unified memory or CUDA malloc managed with some explicit data motion function calls to the CUDA runtime to make sure that the data is already where you want it to be when you need to access it. Okay, and finally, I think this is my last slide about software, and we're just about out of time. Shortly after we announced the Perlmutter system, we also we arranged an NRE partnership with NVIDIA. So NRE stands for non-recurring engineering. This is a separate contract. It's not part of the Perlmutter contract. It's a separate contract with NVIDIA that we had, in which they would implement OpenMP offload for GPUs in their in what's now called the HPC SDK, which was formerly the PGI compiler suite. So that effort has been going on for a couple of years. I think it's just about done, actually. The first version of the HPC SDK, which included the features which were implemented as part of this NRE contract, was released in the 20.11 compiler, which was November of last year. We're now in 21.7, I think, which includes most of what NVIDIA plans to implement in the compiler with OpenMP offload for GPUs. So that's a really exciting addition to their compiler suite, because this was there are other compilers on the system, but I think this one will be very competitive in terms of performance and functionality of OpenMP offload for the A100 GPUs that are on the system. So that's all. The HPC SDK is free to download. You can go try it out yourself if you have access to a system with NVIDIA GPUs, and you can see some of those capabilities that were added as part of this partnership. So that's very exciting. Sorry, I lied. This is my last slide. And I mentioned workflows at the very beginning. So the system's been designed from the very beginning to accelerate workflows. It's not just about doing simulations, it's about supplementing simulations with data processing and pipelines from experiments and other things. So there are lots of innovations that will become available on the system in the future that should facilitate some of those workflows. So we're excited about that. Okay, and like I said, this is a phase delivery. And what's on the left, you see the vertical dashed line. What's on the left is already here, what we call phase 1. And then what's coming in phase 2 is about 3,000 CPU-only nodes, as well as some upgrades to the Slingshot network and a few other, and some more user access nodes, login nodes, and then some more of the workflow nodes as well. So I prefer not to call it, I think eventually it will no longer have a phase attached to it. Eventually it will be Perlmutter. That will be the system. But during this sort of intermediate phase, part of its life, we have to enumerate its different components with these phase numbers. But anyway, so that's what you have to look forward to. So it's an exciting system. We'll be thrilled when all of it's here and all of it's functional and we have it available for users to use. And this is the same summary slide that I started with, so I'll stop here. Kumar, do we have time for? Did you want me to stop now?
There is. No, but there seems to be a question on the chat window. Maybe you could answer it.
Sure. Just to get an idea. How long does it take from the time you finalize the requirements to the time you fix the vendors to deliver them and finally get the system to full production? Let's see. We announced it's on the order of years. It's a long time. You can probably find, I can't quote from memory how long those different phases of Perlmutter took, but usually what will happen is what typically happens in this process is you spend a couple of years talking to vendors and kind of telling them informally, it's like, here's what we kind of expect our workload to look like. And then the vendors will kind of maybe say, here's kind of what we expect our technologies to look like. And eventually you release what's called an RFP, which is a request for proposals. That's the official call for bids. And that goes on for, I forget how long that goes on for, several weeks, but eventually then we spend a while reviewing all the bids and then we select the one that we want. And then eventually we make an announcement, but it's a long time. It's a very long time. And I'm sure anyone at any of the labs who's on this call who's done this before can tell you that it's a lot of work. It's not just slow. It doesn't take that long just because the process is slow. It's because it's a lot of work. Okay, let's see. Do I need to, let's see.
Yeah, the thing, if you still have 2 minutes to answer some of the questions, and then maybe you could hang around when the Aurora presentation starts and keep answering questions that people have.
Oh, sure. Yeah.
Yeah.
Okay, so I'll just very briefly.
No, you still have a minute. Yeah, so okay. you can quickly go through what sure. is there now on the list. Yeah.
Have you thought about using a serif font for Perlmutter to avoid confusion with? Oh, that might just be a quirk of this particular font in this presentation. Oh, you mean on the cabinet art? I hadn't even noticed that there might be an I in there. I was not part of the cabinet art committee that decided all this, so I can't answer that in any detail. I'm sorry. So when will phase 2 be implemented? That I don't think we've not made any detailed announcements about phase 2. Like I said, the timing is unfortunate. There are lots of things I would love to share about the system, but because some of the details are not public yet, I think it's probably better that I don't. But nurse communications will be making a lot of noise when the details become more finalized. So I would just keep an eye out on for sort of very public communications from NERSC about that. Okay, so it is at the bottom of the hour. There is one more question, but I'm happy to stop and I can answer that question in the chat if you like.
Okay, that would be great. And if you could shoot me the slides, I can put them
Sure.
on the Bob's folder so
Yeah.
that Ray can link it. Thanks, Brian. Thanks for doing this. Take care.